Okay, let's start again. I wanted to give you an update on what is going to happen in the next lectures. So note that next week there won't be a lecture. So yes. In fact, next week there will be no normal assignment, but there will be a peer review assignment, right? And I'll talk about this in a bit later. But so the next 3 lectures after this will actually be special as well. So we have 3 invited lectures. So I asked one person who's now in industry and who's using Python in industry to give actually 2 lectures on regular expressions. And that's Jonathan Feinberg, and he will be talking about regular expressions, and he will motivate his problems based on his industry experience. So I hope this will be quite interesting. And actually also the assignment will be motivated, at least by industry. So we will, well, that's maybe a bit far-fetched, but we will create a tool that automatically colors code. So it's a syntax highlighter for Bash. So the idea is you can just type in cat or mycat filename.py, and it will just output your file with syntax highlighting straight away. So I think that'll be quite cool. And also part of the assignment will be to build a diff tool. So it should take in a script that takes in 2 files, and it shows you the differences between the 2 files. Also, again, with highlighting. So I think that'll be pretty exciting. And then, so on the 2nd of November, we have Benjamin Ragan Kelly visiting. And he's actually one of the core IPython developers. So you know the tool that I'm using when I present? This is called IPython Notebook, or Jupyter Notebook nowadays. And also IPython I mentioned before, this interactive Python shell. So he's very much in the core of IPython Jupyter, or the IPython Notebook tools. And so he will give a guest lecture on IPython and will tell us about all the tips, all the tricks and cool things that you can do with IPython. So I think hopefully that'll be interesting to everyone. Okay. Good, but let's start again. Let's go back to our C integration. So far we only talked about C libraries, but with SWIG you can also interface C++ libraries. And actually most of the steps that you do are exactly the same. The only difference is when you call SWIG, you now add this flag -C++. Okay? Otherwise, the steps or the procedure is exactly the same. So down here, for example, the compilation step is exactly the same, with the difference that I now call G++, which is the C++ compiler, rather than just the normal C compiler. So I won't go too much into detail here, but at least I want to show you the example where we interface a C++ function. And so really the difference between a C++ and a C function is typically that rather than using it for the output variables, we use this double *s, which is a pointer to a double. But for the C++ star, we use the reference to doubles, which is indicated by this double and s. But otherwise, they look exactly the same. So imagine we have 2 functions in our implementations, HW3 and HW4, one in C style and one in C++ style. And we want to interface them. And here's how our code, our SWIG interface code looks like. So again, we create the module name here, hello world. We include the source file. We load the type maps because we need to make sure that these S variables are marked as output variables. And then I've used a slightly different syntax here to mark the output variables because I want to use this. So I add the include statement here to just tell SWIG to interface everything I have in my C++ implementation. But the problem now is if I do this is I don't write out the function definitions explicitly anymore. So now I can't write output. Before I had kind of HW1, double R1, double R2, and then double star output. But I don't write it out explicitly anymore now. So instead what I do is I define so-called rules. And these rules are just basically search and replace. And so what it does is it searches for this double star S and it replaces it with the star output. It searches for double and S and it replaces with the star output. And so this is just a syntax that you will often see in SWIG files where you apply these, where you have these replacement rules. Okay. I will actually skip the part about C++ classes because it's pretty, yeah, it doesn't add so much, I don't think. But it's in the, I've added it to the files. I've uploaded them, or I will upload them. Okay, so you might have wondered how this peer review process works for the new assignment. And I just want to give you some information about that. So assignment 4 is due on Sunday. So please make sure that you upload your solutions to GitHub as usual. And after that, we will have a 1-week peer review system. Okay? And so the idea is following. So obviously, coding is extremely useful, and you learn a lot by just coding yourself. But it's also extremely useful to see other people's code and to read it and provide feedback to other implementations. And so it's both useful for the person who reads the feedback, who writes the feedback, because he sees different coding styles. But it's also useful for the person who implemented the original code, because obviously he gets feedback on how to improve his code. And so that's the idea of this peer review that we're going to do. And so basically the way it's going to work is that all of you will be put into groups of either 2 or 3 students, and you will be working together and peer review 3 other solutions, 3 other student solutions. So in GitHub, we will form teams in GitHub. So you will have a special access, all 3 in your team. You will have special access to 3 other student solutions, and that's temporarily. So you can actually access the repositories of these other students, and you can also push files to the students' repositories. And so then the idea is that you open up these repositories and you read the solutions that the student has pushed, and you give constructive feedback to these students. And so this feedback will be in the form of LaTeX. So we will write a LaTeX document where you specify what the student could improve. Maybe the implementation could be written more efficiently or more Pythonic, and so on. And once you've done this, you push this LaTeX file or the PDF file to the student's repository. So at the end, all of you will have a feedback.pdf file in your repository that you can open up, and you get some feedback of your own, about your own implementation. And to motivate everyone to give good feedback, the review will actually give points. So you will get 10 points, maximum of 10 points if you provided a good feedback. And so obviously it's important that everyone contributes equally. So in your group, in your peer review group, you need to kind of distribute work equally. And in case there are any problems, so maybe someone doesn't contribute, then you can just email me. But so this peer review is going to be very self-organized, right? So the way how you distribute it, so you will get an email from me with all the information that you need, and also the peer review, the team that you're in. So you will get the email and the names of your peers. And then you can start emailing each other to organize how you want to do the peer review process. Yes, and if there are any kind of problems with the group setups, you can just always email me. So the deadline is on Sunday, so I will probably set up these peer reviews on Monday at some point. So you have 1 week to do the peer review. And you will also get a LaTeX template that you can use to get started for the review. Yes? No. Other students' solutions, you mean? Yeah. And no, so there's no grading involved. So the way you should see this is, how can you, given the solution that the student handed in, what does he need to do? What does he need to change to get a better solution? Right? So what could be improved in his coding style to make his program better? So this could be, for example, if the solution doesn't have any documentation, then you could state, okay, you should add doc strings to all the functions that you have. Or maybe he or she didn't use Numpy vectorization, right? Then you could add a small section, okay, why don't you, this is probably going to be very slow the way you've implemented it. Why didn't you just implement it with Numpy vectorization? And you can also just show how, show a code example how this might work. So the idea is not to grade each other. The idea is to really help each other to become better at writing programs. Yeah. Any other questions? Yeah.
We will see normal feedback as we have in all the assignments.
Yeah. So what will then happen is that so after you have 1 week to do this peer review, and then you will push your peer review also to GitHub. And after that push, we will correct everything. So, okay, so your assignment 4 that you hand on Sunday will be graded, right? So this will be graded independently on the peer review, and then also the peer review is going to be graded. Sorry, was that your question? Yeah, okay. Any other questions? So, yeah, I hope that everything will be, I will put on some material online, and I will also you should receive emails on all the information that you need. Okay. Who has used LaTeX before? Yeah, okay. It should be fairly, so for everyone who hasn't, as I said, I will give you a template, and it should be fairly easy to get started with. Okay. So the reason why I skipped a bit over C++ is because for our purposes, it's actually more important for you to understand how to interface SWIG with Numpy. So I'll show you this instead. So far, the SWIG interfaces that I've shown you was only interfacing functions where we talked about scalars. Right? So we only passed doubles or floats between Python and C. But for many scientific problems, in particular the Mandelbrot problem or similar ones, we're not just interested in moving numbers, but we want to process entire arrays. So we need to learn how can we pass in basically Numpy arrays between C and Python. And so we need to learn how we can write wrapper code that supports Numpy. And we have a case study for that. So imagine we have 2 tasks. The first task is to implement a C version of numpy.arange. Right? So remember, numpy.arange takes in a single argument, an integer, and then it returns a an array with increasing values. So in this case, starting from 0, going all the way to 9. So that's what we want to re-implement in C. The second task is to implement a C version of numpy.dot. So numpy.dot takes in 2 arrays. One here I pass in A, and then B is of the same length but just containing 1s. And it computes the dot product. So remember, the dot product is just taking the component-wise product of both arrays and then summing them all up. So it's A0 times B0 plus A1 times B1 plus A2 times B2 and so on. Okay. And so as you can see, both these, so the first function here returns a numpy array, and the second function here takes in 2 numpy arrays and returns a double. So now, when we have these implementations, we need to be able to work with numpy arrays. Okay, so our implementation strategy is the following. We need to write C or C++ code that loops over the numpy arrays so that we can compute the dot products. We need to be able to access these arrays from C and C++. And the way we do that is we will use the numpy SWIG extension. And that's implemented in a file .numpy.i. So you can actually download this, store it in the source folder, and then you can include it in the SWIG interface file, which I will show you in a second. But otherwise, the strategy is going to be fairly similar as before. So we will wrap the numpy arrays in C. Then we will write C functions, arange and the dot function that purely works on C arrays. And then we will use SWIG again to generate wrapper codes for these. So I'll show this to you now on live coding. Get it to work. Okay, let's set it up. So this example is in the code snippets in the path SWIG. Oh, this is very hard to read. Can you read this in the back? Is it okay? Yeah, okay. It's in the path mixed/SWIG numpy. Okay, so we have a lot of files here, but not all of them are important. So the first and the most important one are the implementations. So I open up. Let me just see. I think I have it all opened up already. Oh, here we go. Okay. This is my implementation of the dot and the arange function. So I have a file simple.h. So here just specify the input and output arguments in the .h file. So dot takes in a numpy array and a second numpy array. And so here the thing is, when you work with arrays in C, what you do is you need to always pass in 2 things. The first one is the length of the array, so the number of elements. So C arrays, they don't know how long they are. Right? So you need to pass it as a separate argument, which is an integer, so that C knows how long is my actual numpy array. So the first argument here is the length of my first numpy in my first array, and then the second argument here is a pointer to the first entry in my array. Right? So basically, once I have the point of the first argument and the length, then I can just go through all the entries in my array. And this is also the case for the second one. So the second entry here, again, the length of the second array and the pointer to the first entry of my array. And arange works exactly the same way, just so that we have just a single we only have a single array that it takes in, right? Or in fact, this is going to be our output array, because arange returns an array. Now, if you look at the implementation, this is the implementation. So what we do is, maybe let's look at arange. It's a bit simpler. So what we do is we have a for loop. We loop over all the indices, starting from 0, going all the way to the size of the array. And then we set the ith index of the array equal to I. That's it. And so the dot product is a bit more complicated, but it's exactly the same strategy. So we have the result of the dot product is initially 0. Then we loop through all the entries of all the indices of our arrays. We multiply the two components, the ith component, and add it to the sum, and then return the total sum. Okay? So this is our C implementation of both arange and range. Okay, the next step is the SWIG interface file, and that's shown here. So what do we need? The format is like always. We have a module with a module name, so we want our Python module to be called simple, so I stated this up here. And then again, remember the first part is always the actual implementation. So in my case, my implementation was in this file simple.h, so I just include it. But because I also want to have Numpy support, I need to have this additional statement here, so define SWIG file within it, which will load up the Numpy support, which I specify down here. So these are just lines that you can copy and paste. So basically what it does is I include the Numpy SWIG file, and as part of the initialization, I call the function import array. Right? So it's just initialization that I need to do to get SWIG to work with Numpy. But so after I've done this, the exciting part is down here, where I specify, well, first of all, I include simple.h. So this just, I tell SWIG to interface all the functions that I have in my simple.h file. So in this case, it's the dot function and the arange function. And then I have these apply rules. And remember, these apply rules are now being used to specify which arguments are inputs and which arguments are output variables. For which part should be considered input and output variables. And so what I do is I specify, so the first line here specifies a rule that says, okay, so it specifies that I have tuples with a dimension of one array, of a one-dimensional array. So this is what this dim1 stands for. And I have a pointer to the first entry of my one-dimensional array, and that is of type in. So I have a one-dimensional in array and its dimensions, and this is my rule, and where I want to apply this rule is on the arguments int n and double star a, and int m and double star b. And if you go back to my implementation, you can see that this is exactly the naming of the variables that I used up here. So in the dot, I used int n and double star a, and int m and double star b. Right? And these are both input arrays. So this is the rule that basically tells SWIG to use the two arrays that dot takes in as input arrays. The second rule here works exactly the same, just that this is now specified for the arange. And so if you look on the right-hand side here, we have in size and double star r, which is exactly the naming that I used for here for the arange function. The difference now is that arange returns an array. So it doesn't take in an array, it actually returns it. And so now I use, in the apply rule, I use now the wording arg out array 1. So this means that I'm talking about a one-dimensional array, and it's supposed to be an argument, an output argument. Okay, so that's my simple.i file that I've written. And then finally, I've also written a setup.py file, which is shown here. And yeah, this is pretty much a normal setup file, just with some special Numpy includes. So I import Numpy here in the, so basically it's just my normal setup call where I give the module name, the version name, and then I list the extensions that I want to have compiled. In this case, the files that I want to have compiled is the simple.c file and the interface file, simple.i. And in addition, to get it to compile, because now we're using Numpy support, I need to add this include-this where I tell the compiler to also include the Numpy header files. Okay, so once we've done all this, we put everything in one directory. And then if you open up the README, you can see how you're supposed to build this module. And it's exactly the same steps that we always do. So we call Python setup.py build ext, and then Python setup.py install. And in this case, I installed in my local directory. So if I call this, I can actually, let me remove it first so that it remembered that it was already compiled, so I didn't have to compile. Let's see if I can. Yeah. So now you can actually see the compilation steps up here. So here you can see the calls to the GCC C compiler. This is the compilation step, and then this is the linking step. Oh, actually, this down here, this is the compilation of the wrapper. This is the compilation of the simple.c file. This is the compilation of the wrapper file. And then this is the linking file where everything is being linked into one .so file that we can then use as a module. And now if I look at the file system, I can see this green file up here. This is my module file that is a valid Python module that I can then use. And so I have a little test script here. What I do is I import simple and I import Numpy, and I just time the two to see which one is faster, right? So I actually didn't time the arange function, but so okay. So I test the array function. So I call simple.arange for 1 million. So I get a one-dimensional array with 1 million entries. And then I compute the dot product of A with itself and time it using Numpy. And then I time it again using my SWIG implementation to see how they perform. And just print out the results. So let's see if it works and how the two perform. Here we go. So the first good thing is that both of them give the same answer. Right? So that's already a good first step. And then if you look at the implementation, we'll see that my SWIG, okay, so the Numpy took 0.001 second, and SWIG actually took 0.002 seconds. So in this case, my SWIG implementation was a bit slower. And I run it again. This seems to be fairly consistent. So my SWIG implementation is actually, in this case, slightly slower than Numpy. And so you can see that Numpy is often, it's incredibly fast, and sometimes it can be hard to beat. And so now I could see, and maybe I can switch on some compiler optimization flags to get my C implementation faster. But I suspect that the dot product has been highly optimized in Numpy, so it might actually be quite hard to beat. But if you have more complex functions like the mandelbrot example that you're working on, I do expect that you get a nice speed up when you use SWIG, or when you use your own C implementation. Maybe.